On behalf of IEEE MTT Student Branch Chapter, Jadavpur University, I would like to welcome you all to the sixth session, the workshop on different computational electromagnetic techniques and their applications. This particular session is on application of 3D-FDTD framework in MIMO antenna system analysis, and this talk will be delivered by Dr. Debdeep Sarkar, Assistant Professor, EC Department, IISc Bangalore. We'll be starting within a minute. Okay, so it's the time. It's 2 o'clock. So we are going to start the session. This session is already mentioned that it is on application of 3D FDTD framework in MIMO antenna system analysis, and it will be delivered by Dr. Debdeep Sarkar, Assistant Professor, EC Department, IISc Bangalore. We have already introduced him in front of the audience last day, so we are not going to spend any more time in introducing him, as you all know him and you have already listened to his first lecture. So we request Dr. Debdeep Sarkar to please start his session. Dr. Debdeep, please.
Yeah, so can you, just let me first present my screen. Yeah, so can you, I think, see my slides? Yeah, it's visible, right? In presentation mode? Yeah, okay. So, okay, a very good afternoon, everyone. And thanks to Ardhendu and the entire IEEE MDT Student Branch Chapter Jadavpur University team for organizing this workshop. So, I will start my lecture today. I think many of you, I guess most of you have already attended the yesterday's lecture. So the topic is, as you can see, that FDTD method, overview and applications in MIMO system analysis. So what we did, we tried to break it up into two parts. So yesterday, what I mostly discussed about was how to formulate the FDTD update equations. And I took the example of 1D FDTD. So just to show you that what we have discussed so far, so we started from the Maxwell's equations and we gave a brief review of the Maxwell's equations, boundary conditions, constitutive parameters, which are actually needed for solving any electromagnetic problem, to be honest. And from Maxwell's coupled equations, we kind of demonstrated how to actually formulate this 1D FDTD. And then we showed several examples. Actually, I demonstrated how to write that update equations in Matlab, and the basic code excerpts I took from there, and I showed that how the wave propagation is happening. And in the process, I also told about how the analogy with the transmission line situation can be found in case of 1D FDTD. If you recall that we discussed about the EZ and HX component and how they can relate to the voltage and current in a transmission line respectively. So essentially, 1D wave propagation is where we only, it is a kind of constraint scenario where we had this transverse electromagnetic wave propagation. And also in the process, I demonstrated actually through examples these two very important concepts. One is how to implement the source and what is the hard source and what is the soft source. So some of the situations that were arising due to that pulse propagation and all. And also how to truncate the boundary, like why we need these perfectly matched layers at the edge of the FDTD paradigm or whatever simulation space we are having. And because we wanted to suppress the whatever reflections that are occurring from those walls, so they can actually contaminate our desired data. So generally, until and unless we are actually analyzing a kind of closed cavity or a thing like that, we generally use for a, let's say, open problem, especially since I am mostly from a so we have to deal with the radiation boundary and actually open boundary condition. And sometimes if wave is propagating and it is getting like some of the medium is there and some interaction is happening, so all those situation, the entire problem space has to be terminated by perfectly matched layers. So it is a kind of analogous to the anechoic chamber, as I mentioned, that when we do the antenna measurement, we put our test antenna and the entire setup, entire assembly in the anechoic chamber to characterize the antenna. And similar way, like the here we are numerically characterizing our systems. So that is why we need these perfectly matched layers to terminate. And I also talked about how to choose the cell size and correspondingly time stepping. And well, these topics, like it, sometimes it requires like to get a full like mathematical analysis of it. Some rigor is required, and you can consult. I'll show you the books. Maybe yesterday I did not show the books which I personally followed, and there are several other books also you can look up in the internet, books and other YouTube resources. So the important thing is that we need to choose the cell size so that we have a like a proper modeling of our problem space, and we do not give rise to any numerical dispersion kind of issues or any non-physical situation. So that is why it is better to keep very fine cell size sometimes. And but whenever we are limiting the cell size, or we can think that okay, we want to keep it very small, but at the same time our time stepping, it is also actually related or linked via the this stability criteria. I discussed about the current like this CFL. In short, I will not repeat the three names, but the CFL criteria, that we actually had this stability issue. So essentially, what I discussed yesterday was mostly concentrated around this 1D FDTD formulation. And I will talk today how to extend that concept into a 3D situation, because although that 1D situation had some physical, you can say some physical analog, like we had the analogous to the transmission line situation. But to solve a general problem, let's say you are sitting inside a room and you are trying to put a Wi-Fi access point, or let us not go that far, you are talking to somebody with your cell phone, and now you try to see that okay, how the waves from your cell phone is actually radiating into your body. So that is a very general situation that we face nowadays. So if we want to model that situation, of course we have the solvers and all, but it is important from the perspective of this workshop to understand like what underlying principles are there to solve this kind of computational electromagnetic problems. So I believe after today's lecture you will get some idea that how you can personalize or customize your own 3D FDTD code and maybe apply it to some solving some problems. So in my case, because mostly I am, as I am repeating, that I work mostly on the antenna and some part of that MIMO system engineering. So I used this FDTD formulation to solve certain problems. So that part I will discuss. So this is the agenda of my today's talk. So I'll start, as I am repeating, I'll start by showing the simulation of a very basic system, like it is consisting of two dipoles, and how to, and in that case then we have to go to the 3D situation, because now we are going to have a full free space kind of propagation, so we need to go to the three-dimensional view of the system. And then I will illustrate a little bit. So these things, there is no need to be intimidated about all these things. So I'll mostly discuss the concepts, like how I use that. There will not be too much mathematical rigor in today's lecture. So I'll just discuss about how certain analytical constructs like this cross correlation Green's function can be used with conjunction with this FDTD algorithm. And we did some work on this to solve a certain problem that is relevant to this MIMO antenna community and the 5G and all these things that we now recently talk about. And then I will also show how use of this FDTD actually led us to another very fundamental discovery regarding this formulation of this near field envelope correlation coefficient. And after that, I will then show that how, again, we can use this same FDTD, 3D FDTD framework to actually realize or not realize, like lay insight to certain intelligent reflecting surfaces. So this concept is actually very coming up, and it is a promising thing for the 6th generation, or as people say, the smart wireless kind of environment, which will reduce the power consumption and reduce the requirement of active relays and stuff like that. So there has been significant research on this topic. So how we actually did use this FDTD to solve this problem. So now, before going into the talk, I'll want to highlight a couple of things like this research. Although, like, I am currently in ISC Bangalore, but the research part of this work is like mostly done, like this portion is mostly from my PhD, which I did in IIT Kanpur with Professor Kumar Vaibhav Srivastava. And after that, I went to Royal Military College, Canada for my postdoctoral work. And I also spent some time as a international researcher over there. So this part of work is actually done. So from the publications, it will be like apparent to you, and you can look it up and maybe like have your own idea and like carry out research in your own way. So with that, I will start my today's talk. So where I'll start with this simulation aspects of our system of two dipoles using 3D FDTD method. So you can ask me that why I chose this two dipole system. So if you like think about it, I think I mentioned this thing in my yesterday's lecture also, that this is, you can say that this kind of lays the foundation for our entire wireless communication system. If you go back to the early experimental setup that was used by Henrik Rudolf Hertz, I think you can see the timeline. And this is actually taken from this particular link, like this web link. I have taken this figure. So you can see that the early spark gap experiment, it is, if you think carefully, it is basically a system of like the Hertz radiator and the resonator, which were used for creating and detecting Hertzian waves. You can think it of it's a two dipole kind of situation. So you can think about that. So where again, it was not a kind of sinusoidal wave propagation that was noticed at that time. So there was a spark, like you can see, the electromagnetic waves create electric, like this is the receive part, but this is the transmit part. Like the spark actually is producing the electromagnetic waves. I don't know whether that waves is visible here or correctly or not. So how it is produced and how actually this part I was talking, like this was actually the received electromagnetic wave over here that creates the electric current in the resonator and produces a small spark in the spark gap. So this is the physics behind that. And actually it now looking back, like it is almost, you can count how many years back it was. So looking back, we can see that over the last 100 years or more, we have like evolved quite a lot, but everything like started or as far like the history of electromagnetics dates back. So it is based on this kind of experiment, because the mathematical basis that Maxwell's equation provide ultimately to realize the wireless communication systems, the start was from this hard experiment on the spark gap. So that is why I thought that instead of looking into very complicated geometries and all those stuff and how to model them in this particular short duration lecture, it is better to consider a very basic system, that is a system of two thin wire dipoles. Of course, these are like this figure here, it is not Hertzian radiator. I will be operating as the half wavelength dipoles only. But anyway, the idea is from there. So now the point is I have to implement that two dipole system. So just a little bit of recollection that yesterday I considered this 1D FDTD system that had these quantities, if you remember, like mainly this Ez and Hx. So these are actually linked with that. So in the equation, I'm not showing. So, but mainly we had these quantities, and they were like both Ez and Hx along with the Dz and Bx correspondingly. They were the function of y and t. That is, the one is the space variable, or one is the time variable. So in that case, I called it 1D FDTD. Now, of course, time will be there, but now the space part will now become 3D. So you can see that when we go into the 3D simulation, you can quickly, like if you just have a look here, that you can see how much our problem has magnified. So life was very simple here, but now, as it always happens, it is becoming complicated. So now when I talk about the fields, I have to consider, since I am modeling it in a Cartesian coordinate kind of system, I am having that x component, y component, z component, along with for all these four quantities, E, H, D, and B. And not only that, each of these component is actually a function of x, y, z, and t now. So in Matlab or any other solver, if you try to implement it, is basically it will be stored in the form of matrices, like it will be. So the way we will work is generally what people do. We can take a three-dimensional matrix and update it with like time. And unlike the previous case where we had the luxury of like storing the time data for all the time instants, like yesterday when I showed some of those bounce diagram, I actually showed that I have stored the values for all the spatial positions at all the time instants of the simulation. But in this case, in this 3D FDTD simulation case, we really do not want to, like, it is always not necessary to save the temporal data for all the locations. And mostly, if we are trying to find out some meaningful parameters, let's say from the antenna community, I think everyone who is attending the lecture, most of them who are familiar with the concept of the scattering parameters, array parameters. So what we are generally try to do is we try to store those values relevant to the ports of the system. So in this case, let's say I am considering a two-port system here, like two dipoles. I am going to excite it from here. I'll come into more details later. But the point what I'm trying to make is the temporal values I'll be storing mostly relevant to the ports. I'll store the port voltages, or I'll store the currents that are induced here. So nothing is visible here, but when I'll do the complete simulation, you will see that how certain implementation aspects will come into the picture. So how we realize these dipoles? So yesterday I talked about these boundary conditions and all, and something that happened that created the reflections from the wall and all those things. And then we tried to suppress it using the PMLs. But now for this 3D FDTD simulation of two dipoles, the way we do is we enforce this boundary condition. Like, since I am modeling the z-directed dipole, so I'll enforce that Ez will be 0 at the necessary locations. And this will actually represent a thin wire kind of system, thin wire dipoles. So you can, like, to get more insight into this, you can look into the book by D.M. Sullivan, and also the book by Taflov, and there are several other papers, earlier papers back in 1980s and all. You can see them in the IEEE Explore. So the general principle, like Leuber's and Tans and all those people. So you can see that this is generally the mechanism that they use to model a thin wire system. Like, they enforce this boundary condition by making like this Ez equal to 0 at the. So what that means in terms of the computer simulation perspective, that at these locations there will be no updates. Like, I am previously forcing these locations to be at the 0, and I'll put in my source and whatever at other locations, and based on that boundary condition, the fields at the nearby regions will be evaluated. So that will actually give you the actual response. If you get these two dipoles realized by, let's say, some mechanism, some printed thin wires, or in fact practical thin wire systems also, monopoles or whatever. So what happens there in the experimental life, you have to emulate in the computer. So this is the way, like the physical intuition or physical understanding of the system properties will actually help you to realize a model of your system. So in this case for us, you can see it is the entire rest of the thing is free space. I am not complicating my life here. So I am just keeping two thin wire dipoles enforced by this z equals to 0 boundary condition. But well, I have to store all these values in terms of space, and I have to update using the time. So that I have to do. So previously it was very simple to understand the staggered grid. I had this time evolution also. Like if you notice, I am again jumping back and forth. So here it was simple, like it is stored along this array and the edge is slightly offset like this. And this entire thing is actually advancing in terms of the time. But when I come into the 3D, I do not have the luxury actually to show the time advancement, because I can only, like in this figure, I can show only up to the 3 dimensions. Also, that is also essentially it is a 2-dimensional screen, but I am using the projection type of idea to get this 3D view. So if you look back again to that 1966 paper I showed yesterday, so you will find that how actually KE had this visualization of the various field components, and reiterating my fact or my whatever discussion I had yesterday, that you are not going to have your electric field and the magnetic field components at the same location. And you can easily see that why it is so. Like when I mentioned yesterday about the this curl of E equals to minus del B del T, that Faraday's law kind of thing here. So you can visualize like this is a kind of a loop, and forming a loop, like this is EX and EY and again EX and again EY. And if you have this encirculating loop, at the center of that is sitting this HZ. And again, like when we have this knowledge of HZ, let's say this HZ and this HY, like you can see that how that loop for that HH is actually then helping you to evaluate the E component. So if you just take a closed loop, like this is another visualization of the entire thing to clear more clarify the concept. So how the grids are actually staggered in space. So that is again that my main message. And whatever we do, it is actually getting updated. And that updation, the way I defined yesterday, that was a very basic updation scheme. There are other schemes also, but the idea was that it is like in the 1/2 step we had the E, and the next step we had the H. So the entire loop was running in that way. So this is like the thing that we showed, and we will follow, or we followed the exact same procedure. Just the scale of the problem is now magnified. We do not have the 1D matrices, we now have the 3D matrices. But the basic thing, like inside the for loop, whatever is happening, the basic mechanism is still the same. So the idea is this thing will go on and on until like I start my FDTD simulation at certain time, and I fix the total number of iterations that I will go. How to choose that number, I will come later. But I'll decide, let's say I want to run my simulation up to 1,000 or 2,000 steps, 3,000 steps. This loop or this total, if you can see here, this will be followed, and round about here we will put our source, and which in this case is the delta gap. So I think that I have not followed the lectures because I was had some other assignments, but I hope that in the method of moments and the integral equation kind of discussions, this delta gap and frill generator, all those things are already covered. So assuming that, so but here it is basically very simple. Like I am keeping one cell here, and I will put some kind of, I will launch some kind of pulse over there. So that is how I will be actually getting out the parameters of the system. So source insertion will be there, and of course that entire problem space, now if you see that the entire problem space is now inside a kind of a cube. So here in this figure, so I have not shown here, but I have put 10 PML layers. You can put more also. PML layers in the same concept, just in the previous case, I showed how the numerical attenuation is actually happening, the Berenger's PML formulation. So here also I had the same concept, like I put these 10 perfectly matched layers on 6 faces. Like in this case, you can see that there are total like 6 enclosing face for this complete thing. So these are some of the simulation settings that I chose. I chose these cubical cells. Each one is this 1 millimeter, and the total problem space, if you see, it is basically 70 cross 70 cross 70. So it is cubical, as I mentioned. And time step, again, I have chosen based on that current Friedrich-Lewis this stability criteria, 1.8583 picosecond. So in that case, well, I do not have the equation in this particular PPT right now, but I showed that how it is related to that 1 by del x square plus 1 by del y square, 1 by del z square, and the maximum propagation velocity. So based on that condition, we have, like, first we choose that these cells and very fine meshing I did, and I chose this time step, and also total simulation time I chose very large, but while I'll displaying, I'll not be going to that later extent because it will decrease the visualization. I'll show you why. And now what I did, again, recall that spark gap kind of experiment. So I'll do that same thing. I'll put some spark over here, a small excitation pulse in terms of the electric field along that z direction. I'll put at port 1 or port 2 based on my choice. I'll do that. And while I'll do that, I will also terminate the other port which is not excited to a matched load to actually emulate what actually happens in our MIMO systems or whatever. So you can, instead of considering this as a transmitter and a receiver, you can also visualize this as a two dipole system, two dipole diversity kind of system acting in your wireless, in your cell phone, or maybe like in some WLAN access point or something. So these are multiple antenna systems. So I'll come into those things later. But this is the basic concept. So my aim is to now, I want to focus my attention to carrying out this analysis of this two dipole system to find out the scattering parameters for the time being. So what actually happens when I do this numerical experiment? I put this excitation pulse. Let's say I start by exciting port 1 and terminating port 2 by the matched load. And based on this excitation pulse, this is basically a differentiated Gaussian pulse. Yesterday I was showing a simple Gaussian pulse, but this is a differentiated Gaussian pulse. So you can see that it is having a positive transition and again a negative transition kind of thing. And minus, actually the minus sign is keeping that this starting first and is going down. So you can just simply plot this temporal pulse excitation over here. And next, what we do is we try to, like, this is V11. So what this suffix actually mean? So this first one means like this is voltage at port 1 when port 1 is excited. So this way I have to put the number, and this is the voltage received, like voltage at the port 2, voltage pulse at port 2 when port 1 is excited. So I hope that it is understandable to everyone, this notation that I chose over here. And how we evaluate that, how this board voltage. So basically we know that electric pulse, whatever I am launching over here, and here I am calculating all the data. Like I have the data for EX, EY and EZ and all those things. I am not storing the data at other location. I am only storing the value of EZ at this port 2 location. So this is how I am actually, and then multiplying it by this and for performing certain normalization based on the peak value of this to arrive at this result, like this displayable result. And I do not go to the end of the thing, but up to like it runs almost like in terms of picosecond, it is almost around like, since I already showed that this is 1.583 picosecond and this is 4000 delta T. So you can quickly calculate that how much it is actually going. So it will run up to almost this 6000 picosecond or something. So what is happening, I am not showing up to that because in that way this would have looked very like very narrow and you could not have understood. Here also it is not that clear, but anyway you can probably see that this is a differentiated Gaussian pulse over here. And but it is very important to keep the number, like choose that number of simulation steps. Why? Because we actually want these transient effects to die out. So this is, from our knowledge, like I'm doing all this numerical experiment, but we already know how this system would behave, right? Like this is a narrowband system, and you cannot like basically put in a pulse over here and expect that same pulse coming out over here. So it will be some kind of ringing effects will be there because of that narrow banding effect of the pulse. So we had to allow the system to go run on its course, the fields to get updated. So the updation will continue, and we'll store only the values located at these two locations. So we do not store it like if you can see that the total problem space is 70 cross 70 cross 70. So you can quickly multiply and see how many spatial points are actually there in our simulation. And if I try to like save our matrix over here, so it will become 70 cross 70 cross 70 cross 4000. So probably I have checked, but still like we do not have that kind of resource in our Matlab to store this large matrix. But well, if sometime later in future, if that is possible with ease, then of course we are free to do that. But still in current state of art, it is slightly like cumbersome to store all those like values. So what we do is we keep the 70 cross 70 cross 70 matrices and update their values, because that is essential for actually computing the fields. But we store only these EZ values here. So these are the port voltages. But we also need to have the port currents, because until and unless we get, like we know from our basic circuit knowledge that we must get the voltage and current to now next go into that impedance, and from that we will come to the S parameters. So that part we know. So we also need to save the current. So how the currents will actually be evaluated? Again, I showed you the E-grid, and you can remember the Ampere circuital law. Like I have not put that thing over here, but you can imagine like it is curl of
Hello, Dr. Debdeep. Hello. Hello, Debdeep. Can you listen to us? I request all the participants to please wait for some time. Probably Debdeep will connect once again.
Yeah, so am I audible?
Yes, you are audible. Please share your presentation now.
Yeah. Okay. I hope it is visible now.
Not yet.
Okay. Just wait. I'll show you entire screen. So was there any issue? Like I did not understand what.
Just your voice was not coming for last 1 minute. Yeah.
Oh, okay. So I hope I was in this slide, right?
Yes, right.
Yeah. Okay. So I don't know, something maybe I was clicked or something happened. Yeah. So anyway, so what I was telling is we wanted to find out the port currents. So port currents, how we want to find that out? Like we use that our basic knowledge of this Ampere's law. Like we have this integral of H.dl calculated over there. So when we have the, like, let's break this equation into like small parts. So we have this hx and hx component here. So the way we do is this delta x is basically the dl along the x direction, and this delta y is basically the dl, that is the incremental length element along the y direction. So this is, I will not break it down too much, but this is how we are actually finding out the this port currents. So these are the plots for the port 1 excitation. And when we go into the port 2 excitation, you can see a kind of reciprocal response, like and going slightly back and forth. So port 1 excited, this is the thing, and the black represents the like receipt voltage pulse. And in this case, you can see like I am exciting the port 2, and this is like voltage at the port 2. So in that case, I am again having this pulse in the port 2 location, and similar kind of receive voltage V12, like the voltage at port 1 when port 2 is excited. This is actually in the blue color. So this is the same procedure is followed for the current again, and interestingly, you can see how the current actually moves. So this is also another interesting observation, that it is how it goes back and forth. So what happens is you can visualize from the like a dipole physics, like how the charge is actually accumulated at the top and it goes back and forth kind of thing is happening. So the current pulse, you can like have some physical intuition about there also. So now let us say that from our this entire FDTD simulation, we have the data for the time domain voltage and currents. So our next step is to calculate the S parameters. So what we do is we follow this simple approach, that in this for this two-port system, I am saying this is obviously like for the in-port system, you have to generalize and all those things. But for the two-port simulation scenario, we have this M denotes the port number. So we have the V11 and V12, V21, V22, and all those currents, I11, I12, I21, I22, like that. So when we have all this information, we have to find out these four unknowns. Like in this case, we have the Z11, Z12, Z21, Z22 for this two-port system. So what we do is we convert the currents into frequency domain. So this is actually a frequency domain equation. So there is slight, like you have to like be careful about the notation. Like in this case, these plots are in the time domain. But here I have just used the Fourier transform values, but I have not used any other symbol for that. So just for your understanding that these are in the frequency domain. And once we have the time domain data, we can apply appropriate discrete Fourier transform mechanism. So that is a very straightforward signal processing tool that mostly people learn during their undergrads, and for how to like use that time domain data to get like frequency domain data and frequency domain spectrum kind of thing. And so that same process is followed. So once we have the time domain port voltage and port current, we actually get back the frequency domain port voltage and port current, and we can correlate. Now this is valid for every frequency. So we can, once we have the information for the current and voltage at the various ports for all the frequencies, then we can use these kind of tools. So we do two iterations, like once the port 1 is excited and once the port 2 excited. Well, for a symmetric system, you can use certain symmetric condition, but if the system is not symmetric, then you must follow this procedure in this case. So using that, you formulate this like Z parameter equation, and you can evaluate the Z matrices from here by following very simple algebraic like manipulations over here. So I will not show that. That can be like you can chalk it out on your own. That is very straightforward. So once we have that Z parameter values, there are like you can look into any book on microwave networks, where if you know the Z matrix, in this case it is a 2x2 Z matrix, you can find out the S matrix, and for this system we consider 50 ohm to be our like termination impedance. But keep in mind that the update equations we had, there were some kind of transformations we did on the field. If you remember the discussion from the yesterday's lecture, that we divided the electric field by eta naught. So in terms of the impedance also, we like when I am saying that I put the 50 ohm termination, I adjust the boundary conditions such that it is basically the normalized thing with respect to the free space over here. So that thing we have to keep in mind before we convert into S parameters, because the reference impedance concept for S parameters is also very important. So we have to, otherwise it will give us erroneous results. So entire thing is based on how you actually model the system and interpret the data. You keep repeating this part. So we have to, we have come up to the stage where we now have the S parameters. We followed up all the procedures that I mentioned before to calculate the S parameters for this simple two dipole system. But again, we need to validate it. So one way to do is, well, you can put in your simulation in a, if you know SFSS, that's fine. If you know CST, or if you use any other tool, you can just put in the relevant data. Whatever you modeled in your own code, you can just put in that thing in your other system and get back. But here I followed a different approach. Instead of using those commercial solvers, like I wrote the entire code in Matlab itself. So I thought that why not use that Matlab antenna toolbox to actually find out, and it basically operates on the method of moment principle. So I believe that already that has been taken care of in the first part of today's lecture, that how to use that Matlab antenna toolbox. So using it, basically it is very much suitable for analysis of these thin-wire systems. In fact, there is this software numerical electromagnetics code NEC and 4NEC2 and stuff like that. So similar thing, if you use the simple Matlab antenna toolbox and write a few lines code, like this is essentially the code what I have written over there. I chose the dipole element and I kept its certain length and width based on what I chose in my FDTD simulation itself. So I directly took that input from there. And after that, I came into this, use this conformal array element to get a two-element array, and I tried to find out the S parameters of it. So you can see that the beauty of the thing, that whatever we wrote from our basic physical understanding and concepts and all those things, we just simply discretize the system into small grids, and we enforce certain boundary conditions over here. We launched a pulse, we recorded the pulse here, like the voltage pulse over here, voltage pulse over here, current in this port, excited and current in this port. All those things we did from very scratch. What we did was it did not have too much mathematical rigor or anything. We just simply used our own physical understanding and concepts to actually realize or come up to this stage. So it is showing us a very good match. Well, I think I did not print this thing correctly. So it is up to 8 gigahertz what I chose over here. But now, one of the advantage, like I think in the earlier portions of of this workshop also people discussed that one of the advantages you can actually go for wideband S parameter calculation. So for this simple system of two dipoles, I can go up to 30 gigahertz because I chose very small discretization thing. And as I told you, like this criteria that I am having approximately 10 cells per wavelength, that is actually valid for a wide range of frequencies for this simulation. So almost there is very less possibility of the numerical dispersion or any other problem regarding that happening. So whatever current pulses we recorded, based on the transform and based on the processing of that data, we are getting very good wideband data. So I do not have to to get this wideband data. I do not have to come to calculate any other thing. Just that same time domain data I am using to get come up to this wideband data. But for the MOM, I had to do all this discretization at all the working frequencies. Of course, for this system, it is pretty fast and it will take very less time using Matlab also to come up to this data. So this is just for the validation. So if you write your own code, it is very important that you validate and you actually see that some correct results are coming up from your code or not, because otherwise there is no meaning if it is full with data that is meaningless. So that will not give you any practical implementation kind of benefit or anything. So you can see that mostly the patterns are matching.
but there are some slight discrepancies in the S21 levels. So again, that those things can be taken care of. Like we can choose how much. Like I think this part also has been discussed. Like for the MOA, you do not need to enclose the entire thing and calculate the fields at all the points. You just concentrate on the two wires that are basically radiating. But for our FDTD simulation, we have to get into this entire total cubical box, which is actually padded up with PMLs from all sides to stop the waves to interact with the walls and come back and get with the data. So all that considerations has been taken care of. So that actually increases the memory resources and slows down the system. So now the question can definitely you can from this exercise itself, it is quite apparent that for analyzing this thin-wire or only conductor-based systems, of course, MOM and will give you much more advantage, and with the present tools and all, you will get the wideband data also from the MOM simulation. There is no issue with that. But FDTD or FEM, these are coming more useful when we use systems with some of this. As I mentioned, I took the example of a cell phone radiating into your head or radiating into your hand. So in that case, you have to simulate not only these thin-wire, perfect electric conductor kind of systems, but there will be a system of dielectric medium and all those stuff coming into the picture. So in my simulation, I just plugged in, like yesterday, I put in a dielectric slab with epsilon r equals to 10 over here, and I recalculated the S parameter. So doing this is slightly tricky, and I did not find, I might have to look it up a little bit more, but for the Matlab antenna toolbox, I did not find a way to insert that dielectric slab. So maybe they will include that feature, or I will need to look it up to validate the data. But again, I did another numerical experiment on this. Like I put instead of sandwiching it into between the two, this was basically a very symmetric kind of system. So I can put the dielectric slab over here, like near the other dipole. And now I plot the S11 as well as the S22. And of course, the S21 and S12 will be same for this type of systems. So you can see that when I put the dielectric slab near the second dipole, its response is changed, and as anticipated, there is a slight downward shift towards the left. You can see when the dielectric slab is put over there. So you can using this kind of a framework. Of course, it is not there are several solvers available and all, but the beauty of this is just a few lines code of a 3D-FDTD routine. The principle is exactly the same that I followed yesterday, the 1D FDTD, only extended to more memory. Instead of 1D matrices, I now need to store 3D matrices. And of course, the PMLs and all have to be implemented. But you can simply write it, and you can see that your results can be validated by existing commercial solvers. Like this system, you can pretty well put it in a FEM solver like HFSS and check the result, and it will most certainly it will match because the physical principles behind the simulation are all correct. So I started from a very simple consideration. But of course, when we get into more complicated business and come into more real world kind of data, there are several issues. I have just probably tried to put in whatever things came into my mind. But of course, there are much more things beyond this also, like perfectly matched layers, especially for the unit cell simulation. I guess somebody was asking about the periodic boundary conditions also yesterday. Then, of course, there are some of the work on the unconditional stability. So whether we can go beyond the CFL criteria. And as I know, Professor Kumar Srivastava and some student, Dr. Alok Saxena, who is currently in IIT Jammu, they have worked, they are in my knowledge because I belong to that lab. So I know that they have worked significantly on this unconditionally stable FDTD, LOD FDTD kind of development, and then stochastic FDTD and stochastic FEM kind of thing. Here in ISC, I have seen several of the students and with Professor KJ Binoy and other people doing work on this. And numerical dispersion. These are some of the issues that came into my mind, which are actually in the implementation aspects of this complete routine. And you see, like the example that I was keep on mentioning, that cell phone near your head. So there are like you can make very tiny cells, but of course that will again take into change your like memory and all those requirements. So you can go in for adaptive mesh, then how to include circuit components. In fact, in our simulation, I used a circuit component that I mentioned, that lumped resistor kind of thing to terminate the loads. Apart from that, you can use capacitors, you can use inductors, you can use other components like diodes and other active components also. So several people, and that work actually again branches out to the VLSI domain, and signal integrity and all those and issues there come into the picture. And parallelization of the issue of the 3D-FDTD routine that requires, and there were some discussions about it. And I also talked about how to find out the S parameters. Of course, radiation patterns I did not exactly focus in this particular lecture, but from my subsequent discussion, it will be clear that how you can actually calculate the patterns also. I will not show, but I will demonstrate the mechanism to do that, because I will be taking up slightly advanced problems. So, Orthendu, I guess I have 40 minutes of time.
Yes, you have another 40 minutes. Yes.
Yeah. Okay. So with that, like I think I have covered a lot on that. Like you probably now have got an idea like how to do a very simple basic simulation of a two dipole system in the 3D-FDTD, and using that idea, it like should encourage you to write, because it is not like if you take a modular approach, it is not that difficult a problem to do with the amount kind of resources we have these days. Like we have Matlab and we have all those things. And one very good thing about this 3D-FDTD or all the FDTD routines that I have so far discussed is that they are explicit. So you really do not need to go for any matrix inversion or any kind of thing here. So since the matrix inversion thing is out of your way, so life becomes very simple, and like these are explicit kind of equations you can parallelize. In fact, I already showed the parallelizing scheme using this Matlab factorization. But well, this is just a simple that is inbuilt in Matlab, but there are ways to even speed up the entire process. But what I'm trying to, the message that I'm trying to convey is it is not that difficult to write a 3D-FDTD routine that can simulate very basic structures which might be useful for teaching purpose, for your own understanding purpose, like to correlate with the theory and to correlate with the basic physical concept. And when you get that idea, when you can tap into the space-time electric and magnetic fields and magnetic flux and all those data, so you will get a better understanding of what is actually happening. But yeah, I agree that it takes time to develop a full code, but what I'm trying to say is it's not that difficult. Well, with that background, now what I will come to my last leg of my lecture. Well, I will discuss that how a simple code like 3D-FDTD code developed can actually assist you in your own research purpose also. So one of the key area that I made use of this FDTD routine, this conditionally stable and Cartesian coordinate based, very primitive kind of FDTD routine. But I applied that in solving some of the very important problems that are relevant for the MIMO antenna community. And by MIMO, the full form is multiple input, multiple output antenna systems. So some of the problems relevant to that, we actually applied our FDTD routine as to verify our concepts, and some of the things actually came up from the FDTD analysis. So I'll discuss them one by one. So just to little bit have an idea about the MIMO, I think in my other webinars, which are mainly dedicated to the MIMO system, I have used these slides. So you know that we have undergone a significant change from the 1940s to coming to the present day, and there has been a significant evolution in terms of the data rate and other aspects also 5G new radio functions. So MIMO is basically an enabling technology that has assisted us in this change. So the way it actually boosts up the data rate within limited spectrum and of course limited energy like requirements, it can use some kind of signal processing and multiple antennas at your transmitter end and multiple antennas at your receiver end to basically boost your data rate beyond the Shannon's conventional limit. So since I mentioned the multiple antennas in the base station and multiple antennas in the handset, so just to little bit come into again what is more accessible to us, to our handset. So we know that early days in 1980s, the first generation kind of cell phones, they used this kind of antenna where the sleep dipole were used. So the sleep dipole basic concept is like, it is, you can visualize it from a like coaxial cable, the inner conductor protruded out, and there is a sleep kind of structure coming out of that, that is creating the proper balanced current in the system and making the pattern omnidirectional. Because, well, what we try to do in this, this kind of cell phone near that we want to capture the signal from one direction, also radiate into all possible directions. So for the better. So that is what initially people thought about creating the omnidirectional antenna, which is fine. But later on, people started using this diversity concept, where apart from the normal antenna, we had another diversity antenna for the reception, and that can be a spatial diversity, there can be polarization diversity. So we need to ensure that these main antenna and the diversity antenna, there is very less coupling and there is very less correlation. So there starts coming the challenge actually for the MIMO antenna designers, that you have to put multiple antennas. It can sound fine that okay, I'll put, but you have to also ensure that the antennas are not talking to each other. We have to ensure that the antennas, there is the correlation is very less in terms of the port-to-port coupling. Like we talk about the S21, that has to be minimized, and not only the S21, there is that envelope correlation coefficient. So that part I will come. That envelope correlation coefficient is basically the correlation between the fields. That is, and also it is dependent on what type of propagation environment you are placing your receiver. That can be your cell phone, that can be your Wi-Fi access point, any kind of receiver. So that will actually change the way we looked into, like, we cannot only look into the S parameters, we also have to look into the fields, and we have to use the knowledge of the fields as well as the propagation environment to calculate this envelope correlation coefficient. So, well, for two antennas, it is fine. But again, like for multiple antennas, like the things that we take for this like integrated 4G, 5G kind of handset. Yeah, I request all the participants to kindly turn off their microphone, so that will help me to present properly. I guess still some people are not muted, so I request you to do that. Anyway, so what I was talking was that this integrated 4G, 5G handset antennas, to we have to place like all these antennas close to each other. So again, the challenges will increase manifold, and but the basic things remains the same, that we need to ensure low coupling, we need to ensure low envelope correlation coefficient. So then the challenge comes is how to evaluate. So we were talking about minimizing it. So how to evaluate the correlation coefficient in this multiple antenna system? So what is the basic concept of the port-to-port correlation between two antennas? So in a typical spatial diversity system, the port-to-port correlation is fundamentally defined for this receive mode, and it is calculated by two steps. By receive mode, what I'm saying is, you recall that system where I had two phone antennas on the handset, and there is some incoming wave coming onto it, and I want to find out the correlation. So what I do is I actually formulate an equivalent transmit system. And equivalent transmit system, what we do, We determine the radiated far field components E theta and E phi for the individual port excitations by considering the transmit mode and keeping the other antenna port terminated in the match load. So typically the exercise that I carried out using the 3D-FDTD routine, the same thing we have to do in our solvers and all the things, that we find out the radiated field components for the individual port excitation by considering the TX mode and keeping the other antenna port terminated in the match load. Then we also have to know, since I talked about the receive mode, we must know the statistical angular probability distribution and cross-polar discrimination of the incoming wave. So, that is what the two information that we need, and mathematically, you can just interpret those things physically. Like these are the field things that are evaluated, and these are the propagation parameters, and we need to perform this angular integral. So d omega is basically nothing but the sine theta, d theta, d phi, and that is integrated over the entire solid angle. So there are certain issues like in this particular correlation coefficient evaluation. You can see that it is connected to the radiated fields and the incoming propagation parameters. So one way people did was a lot of analysis assumed that we are working in a uniform propagation environment, and when we did that, this p theta and p phi all became 1 upon 4 pi, and this chi parameter became 1. So it simply reduced to the correlation, vector correlation of the far field. And in that condition, people derived, like back in 2003, there was a paper where they derived that if we operate in this uniform propagation environment, we can find out the correlation coefficient instead of calculating all the fields, because 3D field pattern measurement and all those things can become a problem. But if you can go into, you can measure these parameters using your VNA. So if you do that, then you can actually find out the correlation coefficient. So measurement wise, it is fine. Simulation wise also 3D field calculation and doing the necessary post processing becomes tedious. So people use this S parameter kind of thing to find out the correlation coefficient. So there is absolutely no problem with that. But when we the problem comes in a different way, like it is not wrong, but it is not complete also. Like the S parameter based PCC calculation will give you the correlation in the uniform propagation environment. So if you operate in that propagation environment, it is fine. But if you do not operate in that environment, if you are your system, you want to keep in some indoor propagation scenario where the Gaussian or Laplacian or other kind of propagation environments are there. So then the S parameter based formula, well, that will give you some correlation, but that correlation data will not be valid. So this was like, these are some of the research challenges that were posed, that how to then find out the correlation over a wide frequency range if we are working in like non-uniform propagation scenario. So people, what they tried to, like one of the way to solve this problem was, I'm going again slightly back and forth, but what I'm trying to allude you to is that this field-based evaluation, if we can somehow change it to a current-based evaluation, because we are in our solvers, we are mostly working with the currents. If you go for method of movements or other methods also, like we are playing with the surface currents or whatever in the system. So that was one of the key things that Saeed and Professor Antar, Dr. Saeed Miki, he was the postdoctoral fellow at that time. So he devised a way, he formulated this cross correlations Green's function that actually connects the current in the system to the radiated fields. So these are some of the papers, so you can maybe download and you can keep a track of that to understand the basic concept. And also not on this, but a general book that had a small chapter on this part. So this is this new foundations for applied electromagnetics, the special structure of fields. It was published, I think, probably back in 2016 or something. So it is a very fundamentally rich book. So it gives a lot of open threads and new directions to the new research problems. So anyway, the concept of this cross correlation Green's function, it is based on the very well-known electromagnetic principle which we actually studied during our antenna course, and based on the concept of array factors, based on the concept of the Hertzian dipoles. So the general idea is, whenever you find any unknown current distribution in the space-time, let's say you have a sheet of current, or you have a dipole antenna, wire antenna, or you have a printed patch antenna, anything, you can actually discretize the radiating current in that system in the form of small infinitesimal dipoles, or you can estimate the radiation from that patch or slot or whatever by a combination of small infinitesimal dipoles located at certain locations, and some optimization routines you can use. So what the idea is that this infinitesimal dipole modeling itself, that is another thing. In fact, Said worked on it with Professor Ahmed Kishk during his PhD, and of course it is also used by many other researchers, this infinitesimal dipole modeling concept. So it is based on that and it is actually nothing but the spatial sampling. Like, these Hertzian dipoles are not actually existing over there, but I am just taking the total spatial distribution in the form of these infinitesimal dipoles. So once we break it down, so I will not again go into the mathematics of the entire thing, but I'm just trying to highlight the concept that this field-based equation is actually transformed into a current-based equation, where if we know the current in the system in the form of infinitesimal dipole, and we use this thing, this cross-correlation Green's function tensor, CGF tensor, which is our C bar. So there is a way to calculate its various components. So you can actually use this CGF tensor. So why is it a tensor? Because it has all possible 9 combinations of the relative polarization. So if your current has the X, Y, and Z component, one of the current, and other current will also have X, Y, and Z component, then you have total 9 components. So there are ways to derive that. I am not going to the derivation on all those things. But the importance of the CGF in MIMO system analysis is it gives us a way to now interpret the radiating currents in the MIMO antennas for various port excitations. And we can use this CGF with the currents evaluated in the system through any computationally electromagnetic tool, be it a FEM solver, be it a MOM solver, be it a FDTD solver, to actually find out the envelope correlation coefficient for various propagation environments. So one key thing, I again come back here, that to just allude you to the fact that if we look into these tensor components for the most general case, it actually imbibes the various propagation parameters over there. So if you have the knowledge of the propagation situation prior, you can plug it into your simulator and you can optimize your antenna based on that. You can keep on calculating the correlation for it. So this gives us a route to go into designing of the optimal antenna systems for using this for being applied in these MIMO systems. So anyway, what my objective was not to go into that design side of things, because that was already taken up by Said and some of the other groups like Crozier and some of the other researchers that worked on the same topic over there. So during my PhD, I worked on a way to integrate this cross-correlation Green function with FDTD. I called it this FDTD CGF algorithm. And the idea was we wanted to find out the wide band envelope correlation coefficient at a single go, and which was at that time not readily available in the HFSS or CST. In fact, I think even today, the wideband ECC computation requires the field-based thing, which is fine. It will help you in the design process and all. But if you use this as there are ways, and probably this will be implemented later on, to use this algorithm of using any time domain current. You can use our algorithm and the knowledge of CGF to find out the far-field envelope correlation coefficient. So these are the papers that we did worked on a couple of transactions a few years back, 2017 and 2018, where the idea was pretty simple. We have, I showed how to calculate the port currents from the FDTD simulation. But we can actually tap into some more spatial locations also. We can encircle the magnetic field around those thin dipoles, and we can find out the total current distribution on the thin wires from the for the pulse excited situation. So we have the space-time current distribution. This will not take too much memory. Like these are, if you let's say discretize your dipole by 20 points or maybe say 50 points. So this will be a 50 cross the number of time steps, whatever you are actually, how many time steps you are simulating your FDTD code. And similarly for the other port excitation. But one key thing is this is not the current on the dipole 1. This is the total current on the dipole 1 and the dipole 2 for the port 1 excitation. And this is the total current. So maybe in the next figure, I'll explain that part again. So I found out two ways to actually calculate the wideband ECC. So first way is pretty obvious, that we can take the Fourier transform of the current and then essentially gives us the wideband frequency domain data. So there was not much innovation in there. So it is just the straightforward process that you get the time domain space-time current distribution from the FDTD simulation. You take Fourier transform of the current and you do the frequency domain post-processing of these radiating current and the CGF components to come up to the wideband far field envelope correlation coefficient. But another thing which was the main our contribution, that we found out this FDTD CGF-TD algorithm where we did some kind of time domain signal processing. And there, what we did was that we first found out the angle-dependent time delay from the location information. For interested people, I would suggest them to follow this particular paper because this is just an extension of that. It is a communication article actually. The main full transaction paper is this one. So we found out the angle-dependent time delay from the location information, and then we use the time domain post-processing using the current information, the CGF, and the angle-dependent time delay. And finally, we get a complete time domain like quantity. And using that Fourier quantity, we do the Fourier transform of that combined time domain correlation thing. So this actually resulted to be very fast as compared to this one. And this was like we reported the various issues like the error and whatever things will come based on how you discretize your angles and stuff like that. So there were several intricate things that were discussed on this particular paper. So we had to validate, of course, and I fell back to the standard system, which I think this part, due to the initial discussions of today's lecture, you can pretty much guess that that was the same two dipole system. That at that time I did not use the Matlab toolbox, I used HFSS to validate it, and it was probably designed for some other frequency range also, just by changing the length, nothing else. So we in the FDTD model we also used at that time 21 discrete current elements per dipole. But still, what we found out that this FDTD CGF-TD, it computes the wideband ECC with very high resolution in less number of time. Like I'll explain, like what will happen is in HFSS, we had these discrete frequency points being calculated one after another. So if you increase the fineness, like if you try to get the spatial correlation in more resolution, then the time actually magnifies a lot. But in our case, just from a simple simulation, you get the time domain data, and just by the second, you will get that wideband correlation. So we discussed those time aspects. But well, the reviewers will keep like asking you questions to validate your algorithm and all, and that happens. So we went on to validate our algorithm for several situations. One of the situations was whether we can actually analyze the multi-band antennas that are used for modern day systems. So we used like a very again concept on the two dipole itself, like we loaded the dipoles with LC resonators. So basically the concept of the trap loaded dipoles, like there are a group of people, even we did some of the work claiming that these antennas to be metamaterial antennas and stuff like that, but it is nothing but simply resonator loaded antennas that will give you the multi-band response. The resonator can be embedded in the dipole. The resonator can be kept near that in the close proximity of the dipole to get the multi-band impedance matching. So the radiation profile remains the same, but you can match it at different frequencies and you can get that multi-band response. So in those kind of system also, our code actually we could find out very like fine resolutions of this system. And then we extended that thing for various propagation environments also, like Gaussian uniform environment. We evaluated the antenna for various incident angles, keeping or for like different of this incoming angular spread and all those things. So we did all those kind of stuff to show that our algorithm is actually working. And finally, people are also like concerned that whether it can be only applied for the wire antenna systems and printed antenna. So again, we demonstrated that since the algorithm is based on very fundamental principles, it is possible to apply it to any kind of thing. So that was the kind of outcome of the research where we tried to integrate the cross correlation Green's function to the FDTD routine for this far field envelope correlation coefficient computation. And it is a like nice thing, like it is a kind of add-on to your current solvers. You can interpret your things and do stuff like that. And maybe in later future, some other people who are developing CEM tools will just simply include this algorithm into their routine, and that will give you an additional dimension. So the research part is done and it will be applied. But another thing that came up as an outcome, and we did not really plan for it, was this kind of, I would dare to say, it's kind of innovation or for this new metric, which is the near field envelope correlation coefficient. So I will come into that. I guess I still have around 15 to 20 minutes of time, so I think it should be okay. Yeah, so this near field correlation, I'll just hint at that, how it came into the picture. So when we introduced the definition of the far field correlation, we considered that the antennas are illuminated by some plane wave from space, and that is how we built up the entire definition of correlation. Like we assume that our antennas are hit by uniform plane waves, and some currents will be induced in the ports, and from there we will get the port correlation, which is fine. And if we are working in the far field regime, but will we always work in the far field regime? That is what we say. Or whether we will come into the radiating near field zone also. In some situations, can we come even close to the reactive near field zone? So those are the kind of things that present day communication system deployments are posing to the researchers. Like previously, we could have simply considered our array theory and all those things, but remember, all those things are valid for the far field analysis. But when we are talking about the ultra dense networks and nearby several proximity to let's say a massive MIMO base station, all this kind of thing that people are talking about, eventually we need to rethink our strategy to evaluate the correlation. And here again another point comes that I will simply call, if you read any communication book or anything, they simply call that correlation coefficient. But correlation coefficient between what? We assume that when we are in the far field, electric and magnetic field components radiated from the antenna, they are kind of I dare to say that a kind of a proportionate kind of relation is there. So what is actually challenging when we come to the near field, that the field components, electric field and the magnetic field components, they are not exactly simply related like that. So it was interpreted that we will definitely have two types of correlation coefficients. One is the electric field correlation coefficient, one is the magnetic field correlation coefficient. So that was a kind of conjecture that we had. That was a kind of conjecture that we had, and we worked on that. But it was not that we had the conjecture first and we did the simulation later. Actually, I was doing some simulations on this two dipole system that I actually showed you, and from that we saw, we investigated, and it was kind of a result from the numerical experiment where properly interpreted with a theory. So Said actually did that theoretical framing for this thing, but it was based on the numerical kind of experiment that I had first. So what we actually did was we found out, we followed this way, in this case I took this horizontal kind of dipole thing. These are the two dipoles, you can see the black wire kind of thing. And what I thought was, instead of taking a far field correlation sphere, like when the correlation sphere is we consider that waves are coming from a very far direction. If we consider that the wave will come from a very close proximity to the antenna system. So we introduced this concept of near field correlation sphere. And like this concept, you can have a look into this particular paper, which was published last year in July, that near field cross correlation analysis for MIMO communication system in IEEE antennas and wireless propagation letters. So the idea was that we had this near field correlation sphere, and we took the electric fields on it, magnetic fields on it, and from that electric and magnetic field components, we actually found out the correlation using the formula that I have shown here. So this is actually the thing, like the two antennas, they are surrounded by a correlation sphere, and on the sphere, we are actually sampling out our electric and magnetic field components. So we are essentially using more memory. Like I was telling you that we will only store the data at the ports, but in this case, I used the routine from Matlab because anyway, the values are getting evaluated. So when we fix the radius, and we can choose certain angular intervals, and we can sample out the electric fields and these various locations. So basically, this is how, like for a fixed R, we take various theta and phi values and take the time marching of this data. So, and we followed that same differentiated Gaussian pulse kind of excitation. And the results were pretty interesting, that we saw that the inequality between the electric and magnetic field correlation coefficient, when we, let's say, operate with a correlation sphere of radius 9 delta. So that was the idea. Like you can see that when we take a 9 delta kind of thing, you can find out the electric correlation coefficient. For dipole 1 excitation, you find out the field. For dipole 2 excitation, you find out the field. Let us assume the uniform thing. And from the electric fields, you will get one correlation coefficient. From the sampled out magnetic fields, you will get another correlation coefficient. And this will come, like you can verify it in other solvers also, they will not be equal if you bring the correlation sphere very close. But if you go far and far away, so eventually it will converge, like those two things. We check that from rigorous like numerical simulations on the system, that eventually it converges. But when you come close, so it is important to define the near field correlation coefficient, but the general communication theory books are not having that concept. So that thing we are planning to keep it or introduce it in more formal way sometime later. So finally, a little bit on the other research, these are some of the, I am talking about the research directions on the MIMO antenna system that we do using FDTD. So far I have talked about this handset or access point system where close by some multiple antennas are there. But of course, in the 5G, massive MIMO is a very important concept, and also as I was talking about the 6G, will be going into the intelligent reflecting surfaces. So this is just in a nutshell the idea of massive MIMO, that we have a large number of antenna elements and arrays, basically a large phased array kind of thing, and dedicated transceiver integrated directly to each antenna elements for maximum phase and amplitude control of the aperture. Of course, we have to take into account other aspects. And when I talk about this large MIMO system, it is very important that we recall the inception of this concept, like massive MIMO, large MIMO systems. And interested people can, of course, look into the book by my senior colleague here, Professor Chokalingam and Professor Sundarajan. So you can have a look into this book. So it is basically used for the beamforming, 3D beamforming and all those stuff. So I will not come into the details of that here. But what I attempted was, of course, we know that for this channel modeling in these massive antenna arrays, people have already well-established tools like this ray tracing and all. So I was learning a little bit about that, and then I thought that why not, since of the number of the amount of codes in our system and the memory and all, these are getting amplified day by day. So we can now at least think of attempting a large channel modeling kind of problem. Early times using 2D-FDTD routine, people sometimes validated the channel modeling thing. But I thought that why not? Let us try what will happen. Like it will take long time, of course, and I am not I'm not basically use it for some practical channel modeling application. But at least for the research perspective, I'm sorry for the noise. I think there is some drilling thing going on in the office. So I hope I am audible properly. Yeah, so just what I was telling, that this like large MIMO system kind of simulation, I tried to attempt using our routine, like FDTD routine, and it took a lot of time, and we followed the channel modeling procedure where each of the user equipment was excited by this modulated Gaussian pulse. And from that, we tried to interpret, like I validated with the conventional ray tracing routines and all. So it is possible. It is time consuming, memory consuming. Nevertheless, it is possible. We did, this was just an academic kind of observation that I found. But later on, I used that framework to work with this particular system where we have the massive MIMO with frequency selective structures. So frequency selective structure, we have we can model it using these wire grade FSS kind of systems. And this thing I will not go into the too many details because I guess time is also limited. But the engineering the eigenspace structure of massive MIMO links using these FSS, this we already did some research on that, and this was not like readily attemptable by the ray tracing system because it has a lot of rich electromagnetic dynamics in that. So we use the pointing flow kind of thing to visualize and use the you can look into the paper to see how we got these eigenvalues for the channel and all. I will not bore you with the details here. But what I like to finally point out is this intelligent reflecting surface concept, where we can actually use a meta surface with reconfigurable unit cells to change the reflection coefficient and change the scattering coefficient. All the things we can now have a control over that. So when we have that thing, we can actually go towards this smart wireless communication. So this is another paper that I would like to bring to your attention, that smart wireless communication by IRS, and this is a in this year itself, it is coming out in the IEEE Communication Surveys and Tutorials. Of course, there are many other papers. So we use the FDTD framework, electromagnetic framework, for using this reconfigurable intelligent surface to control the massive MIMO channel characteristics. And still some work is going on in this domain, and we'll report it in sometime later. But this was reported in the European conference on MIMO. And finally, before I wrap up my talk, so I talked about several applications of the FDTD with respect to this MIMO, but there are some of the results that we had on the energy of the antennas as well, regarding the energy around the antennas. So that is, you can have a look into these papers. I will not probably at some other stage I will discuss about these things. But this will come out in the next year's magazine, and this is one of the transaction papers that came out of the energy research. So it is important to look into the near field energy distribution that is not available from the standard MOM or other routines. We did that with FDTD. We introduced some concept of pointing localized energy, and that we reported, and maybe in some other forum I will discuss more on that. So with that, I think I'm almost on time. So I'll wrap up my talk. So I talked about the 2D, true dipole kind of simulation using 3D-FDTD. Then I discussed about the FDTD CGF routines and how you can perform the analysis on the space-time currents to get the DCC for various propagation environment. Of course, we need more printed antenna test cases. We need the also extend the near field correlation model. So these research are ongoing, and of course we focused on this reconfigurable FSS based channel manipulation thing. So these are some of the clues that what you can do, because this is a computational electromagnetics workshop. So my idea was that if you at least learn one of the routines, computational electromagnetic routines, let's say FDTD, let's say FEM, let's say MOM. So if you have your own routine, that can not only enrich you in terms of the knowledge of electromagnetics, that can also help you in conducting some fundamental research. So that is one of the message that I wanted to convey through this final segment of my talk. So with that, I'll thank you for your attention and we'll be happy to take on any questions. Thank you.
Okay, Dr. Debdeep, on behalf of IEEE MPTS Student Branch Chapter, we would like to thank you for such an insightful talk. So we have received some questions, so we are going to read those for you.
Yeah, sure.
Before that, I request other volunteers to share the attendance link for this particular session. And after this session, we are going to have another brief session on IEEE MPTS Student Branch Chapter activity and IEEE membership booth. Okay, Debdeep. So I'm going to the. How much time is taken to execute the program of S parameter for the two dipole system and two dipole antenna system for wideband frequency? Is it possible to share the code?
Well, I think I will make it available at some point of time, and I will definitely share the link with maybe you, and you can forward it to the. But not right now. I am still working on it to make it properly shareable. Now, regarding the time aspect, it for the wideband simulation, it does not take any extra time. Whatever time it is only for the FDTD, like time domain current calculation part. For the Fourier transform, it is the same it is the same time as it is taken for the narrowband with respect to the wideband. So that is because that is one of the advantages of the FDTD method. Like unlike MOM, for the MOM thing we had more time to do the wideband simulation, but for the FDTD the time is constant.
Okay. Next one is. Sir, what do you mean by diversity gain of MIMO antenna?
Yeah, okay. I think, this is probably slightly not relevant to the CEM workshop, but still I will just try to address it very shortly. Generally define it when we find out the envelope correlation coefficient, then we do that manipulation on that, like square root of 1 minus mod rho square kind of thing. We calculate it is just another metric to denote how much diversity the system has. And if it is, let's say, 4x4 MIMO antenna, so for the various port combination, you have to find out the ACC. From there, you get the diversity gain. And it basically means how many, if your diversity gain of the system is better, so the ports are less correlated. And so you will get more enhancement in the whatever data rate you intend to achieve. So the better the diversity gain, the more from a single user MIMO kind of point of view, the better your performance.
Okay, thank you. Next question is how massive MIMO antenna can be used for automotive applications?
Yeah, well, I think this is also not exactly related to the FDTD, but but it can be used. I would suggest the person to look up to some work on the vehicular radar, or maybe used up the phased array in vehicular application. So massive MIMO, as I iterated, that it is basically just the extension of the concept of large phased array. So that is it.
Okay, so I'm going through another related question. How to introduce computational electromagnetic subject along with advanced antenna theory for PG and research scholars as a coursework?
Yeah, so I think that is in a way precisely the objective of this workshop itself. From my experience, I am not a very big expert on this domain, but from my little bit of experience using this FDTD routine, what I can see is you can I have seen the way the computational electromagnetics courses are framed here in ISC. So they have a module on the method of moments, they have a module on FDTD. So it is possible based on but of course the instructor has to put in effort to how to introduce that topic from very, very fundamental. So what I would suggest is it is important to correlate with the Maxwell's equation and the boundary condition to the actual real life problems and where we are going to use those things. And in the process, you will learn about how the different aspects of the coding are actually influencing your results. So I would reiterate something that my computational informatics course instructor said, that it is not like just like any other programming course. You have to code your own routines. Only then you will get an understanding of the system. So it is essentially that kind of an approach it should be taken, and it is already taken in many places in several IITs and NITs and other institutes. It is already there. So that's it.
Okay, though not related question, but the last question came from Aditya Goyal. He's asking that is there any PhD position available?
Well, yeah, like we are currently expanding, but we have to follow the norms of the institute. So any interested candidate can email the CV to me, and if some possibility is there as a research associate or anything, then I can take a look. And there are certain windows like midterm and other windows that are again available in the ISC website. So I would suggest any interested candidate to follow those links. And yeah, that's it.
Okay, so thank you so much. On behalf of IEEE FDTD Student Branch Chapter, we would like to thank you once again for your valuable contribution. And this is the second time. Initially, earlier in February, we had a physical meeting at Jadavpur University with you.
Yeah, definitely. Sure,
okay,
I'm also looking forward to that. Yeah, thanks again. Yeah.
Okay, so I'll give you a call or I'll write you soon. Okay.
Thank you. Sure. Thanks a lot, Arvind. Yeah.
Okay.
Thanks.
Bye. For the participants, I would like to inform that within 10 minutes, we will be having our next session, which is though not technical, but we'll be having an overview of the activities that we have carried out throughout the year. And we are also going to tell you regarding the IEEE membership joining and the basic benefits that you can get. And if you need any help, you can ask us. We will try to help in that regard. Thank you.